AB Calculus, Section 1.4, day number 1, trigonometric functions and their inverses. Our objectives in this video are to talk some basic trig, some special right triangles, 45, 45, 90, 30, 60, 90, sine, cosine, tangent, as well as some trig identities and solving trig equations. So let's get to it. You can see in this image here, I've got this angle theta in quadrant 1, where this point here I would call the point xy, pretty generically defined, where the length here along the base would be x and the vertical length would be y. The hypotenuse here, the red length here would be, we could call r, and therefore any angle in this orientation, we could find the sine, cosine, tangent, cosecant, secant, and cotangent using the lengths that are provided on the right triangle. So the sine would be the opposite over hypotenuse. So that would be opposite side over hypotenuse, y over r. Cosine would be adjacent over hypotenuse. Tangent would be opposite over adjacent. And then each of the subsequent functions beneath would be reciprocals of the ones above. So for sine theta, its reciprocal is cosecant theta. So this will be r over y. Cosine theta is reciprocals with secant, which would make secant theta r over x. And then cotangent and tangent are reciprocals, which would make cotangent x over y. Now, cosecant can also be written as 1 over sine of theta. Likewise, in the same way for the others. So 1 over cosine theta for secant, and 1 over tangent theta for cotangent. So that's some basics of right triangle trig, and we're going to utilize those here in a little bit. So let's look at a few examples, and let's talk some special right triangles. So if we're in the unit circle, any hypotenuse in the unit circle will be 1, right? So 45, 45, 90, if we use Pythagorean theorem, we would find that the lengths would be 1 over root 2. Okay, so that's the ratio of sides. If I were to double it, I would get, if I doubled 1, I'd get 2. If I doubled 1 over root 2, I get root 2 over 2. And root 2 over 2. If I were to triple it, and so on, I can scale it to whatever length I want. However, when we talk about the examples here to the left, we will always be using the unit circle ratios for those sides. Okay, for a 30, 60, 90, this would be our 60-degree angle. Here's our 30-degree angle. If the hypotenuse is 1, the short leg's ratio to the hypotenuse is 1/2 of that length. And the longer leg would be root 3 over 2. Okay, now when we're in the unit circle, again, when we divide, so if we're taking opposite over hypotenuse, we're always dividing by 1. So really we're just looking for the y value or the x value if you're in the unit circle. So as I look at, for example, example 1, the sine of pi over 6. Well, pi over 6 is an acute angle. Right, and it's 30 degrees. So if I were to look at my 30-degree angle, and if this were in the unit circle, that would be a 1 for the hypotenuse. The opposite side would be 1/2, and the adjacent side would be root 3 over 2. So the sine of pi over 6 would be 1/2 over 1, which is 1/2. Now the sine of 7 pi over 6 is very similarly related, except this falls in the third quadrant, just past pi units. Here's pi units. Okay, this would be the point -1, 0. And this reference angle right here, if this angle of rotation is 7 pi over 6, then the reference angle, this blue angle, would be pi over 6. So it's the same triangle, except the values are going to be slightly different because, well, it's in a different quadrant. So we're going to go left, negative root 3 over 2, and down 1/2. The hypotenuse, again, is still 1. So the cosine of 7 pi over 6 is negative root 3 over 2 divided by 1. In example 3, the cosine of negative 3 pi over 2. Now the hard part about this problem is actually where does that angle land? And negative 3 pi over 2 would be a rotation clockwise, 3 pi over 2 radians, which would put us at this point. So at this point, we would have the point 0, 1. Now in the unit circle, as we've noticed so far, the cosine is always the x value and the sine is always the y value. Therefore, the cosine of negative 3 pi over 2 ends up being the x value there, which is 0. Okay, 11 pi over 2, where does that land us on the unit circle? All right, here's 4 pi over 2, that's 2 pi. So this is 0, or 2 pi, or 4 pi, or 6 pi. All right, so that's 4 pi over 2, and that is 8 pi over 2, and that is 12 pi over 2. So it's going to be somewhere in between 4 pi and 6 pi. My guess is that it's going to be over here, where this is pi, or 3 pi, or 5 pi, or would that be 7 pi? All right, so this would be 6 pi over 2. This would be 10 pi over 2. This would be 14 pi over 2. Okay, so let's see. I'm guessing then it's going to land right up here. All right, let's see. This would be 4 pi over 2. Then if I go around again, that'd be 8 pi over 2. Now I'm going to add another pi over 2. I'm wrong. This would be 9 pi over 2, 10 pi over 2. That would make this 11 pi over 2. Finally, we got there. All right, so this would be theta equals 11 pi over 2. So what would be the tangent there? Well, the tangent of any angle we said was the y value over the x value. So let's look at that point. That point is the point 0, comma, negative 1. If I took negative 1, which is the y value, divided by 0, that actually doesn't exist. So there you have it. The tangent doesn't exist at 11 pi over 2. All right, let's keep on moving. Okay, let's graph a few trig functions here. So let's start with sine. The sine function, sine of 0 is 0. Sine of pi is 0. Sine of 2 pi is 0. So here's 2 pi and 0. Now, sine will have a range of negative 1 to 1. So the possible maximum output of 1 and minimum possible output of negative 1. And those are attained at pi over 2. That's where sine is 1. And at 3 pi over 2 on the interval from 0 to 2 pi. So our function for sine, one of my better sine functions, would look like that. Now if I were to sketch another period, you'll notice that, as we talked about in a previous lesson, the sine function is odd. Therefore, sine of negative x is actually equal to negative sine of x, according to the odd function rule. Okay, cosine, of course, cosine of 0 is 1. Cosine of 2 pi is 1. And cosine of pi is negative 1. Okay, at pi over 2, cosine is 0. At 3 pi over 2, cosine is also 0. Not my best function after drawing a really good one on the sine function previously. So you can tell, based on the symmetry of the graph, that cosine is even. Therefore, cosine of negative x is equal to cosine of x. All right, let's look at tangents. Tangent, as we know, has asymptotes. The the tangent doesn't exist at x, oops, that should be a theta. Theta, well, I guess we are in terms of x. At x equals negative pi over 2, and at x equals pi over 2, as well as every pi unit. So at x equals 3 pi over 2, and x equals negative 3 pi over 2. All right, so the graph of tangent looks like this, and it repeats itself every pi units. So with sine and cosine, the period length, when it starts to repeat itself, is 2 pi, but with tangent, it's pi units. Therefore, as you can see here, tangent is an odd function. So check this out. Tangent of pi over 4 is equivalent to the opposite, the opposite of tangent negative pi over 4. Those are 1 and negative 1. Therefore, the tangent of negative x is equal to negative tangent of x. We'll talk more about graphing and all that stuff later. But here you can see clearly that within that interval, here is the graph that we're looking at. And of course, all three of these functions are not one-to-one. So when we talk about their inverses in the next lesson, we're going to have to restrict their domains in order for them to pass the horizontal line test. All right, let's move on. Okay, identity work. This is your favorite pre-calc topic. I know it is. Trig identities, here they are, all of them. All of the ones that you need to memorize. Okay, and you got to get used to using them. So let's look at the example we've got down here. Solve for x. So if I'm going to solve for x, I need to know my identities. And the identity that I see here is sine 2x. And sine 2x, as you can see above, is 2 sine theta cosine theta. So I'm going to write this as 2 sine x cosine x, and then I'm going to subtract the sine x over from the right side and set the right side equal to 0. Okay, so now what I'm going to do is I've got to consult, different options. In this case, I'm going to use a factorization model. In some cases, you might do, a slightly different method, but factoring will work for this. Now, using the zero product property, if the product of these two items, the green and the blue expressions, is 0, then either the green expression equals 0 or the blue expression equals 0. And then we solve. Well, where does sine x equal 0? Well, if I look on the unit circle, that's where is the y value equal to 0? Well, the y value is equal to 0 here and here. All right, so this is the point in the unit circle. This is the point 1, 0. This is the point negative 1, 0. And you can see that the y value equals 0 in both cases. Now, within 0 to 2 pi, that happens at 0 pi and at 2 pi, as well as at pi units. So this yields answers of 0, pi, and 2 pi. While the other, cosine of x equals a half, that happens at a few values. It happens at this special 30, 60, 90 triangle. It looks like it might happen there, but actually it only happens at 2 of these. Now the cosine is the x value. So the x is negative in quadrants 2 and quadrant 3. So those angles are not going to be appropriate here. So at these 2 points, this is the point 1/2 root 3 over 2. This is the point 1/2 negative root 3 over 2. So what are these angles, right? This angle here in quadrant 1 will be x equals pi over 3. And the angle in quadrant 4 isn't negative pi over 3. Because we want the angle between 0 and 2 pi, it's going to be the angle 5 pi over 3. Therefore, the solutions in this case are x equals 0, pi over 3, pi, 5 pi over 3, and finally 2 pi. All right, there you have it. That's using some identities to solve a trig equation. Let's continue. All right, let's continue this similar process and let's solve in this case. Now, tan squared, there's a couple different ways you can go. Some are more complicated than others. What I'm going to do is take the square root of both sides. So that gives me plus or minus the square root of 1. So the tangent of x equals 1, or the tangent of x equals negative 1. Well, where would the tangent equal 1? Now, if you think about tangent, that's y over x. So when would y over x equal either 1 or negative 1? It would be when this angle here is 45 degrees. Okay, so if I look in quadrant 1, of course, that would mean that x equals pi over 4. And also in quadrant 3, I'll also get a positive 1, right? Because x and y in this case are both negative. So in quadrant 3, that would be the angle 5 pi over 4. Now tangent is negative in quadrants 2 and 4. Therefore, I'd find the appropriate pi over 4 scaled angle in each of those quadrants. In quadrant 2, it would be 3 pi over 4. And in quadrant 4, it would be 7 pi over 4. There would be our answers to tan squared x equaling 1. Okay, let's look at example 10. Example 10 says cosine squared equals 1/4. If I again use the similar method and, it looks like I messed something up in example 9. I just realized it. Good catch. I don't need answers outside of 0 to pi. So 0 to pi would only be quadrants 1 and 2. So I am going to, looks like nix 5 pi over 4 and 7 pi over 4. So my answers are simply pi over 4 and 3 pi over 4. Good catch. All right, let's continue with the example number 10. Okay, taking the square root of both sides, I get cosine x equals plus or minus 1 over the square root of 4, which is 2. Okay, so the cosine is 1/2, and I want all values between 0 and 2 pi. So cosine is 1/2 at each of these angles. All right, each of these reference angles are going to be 60-degree angles. Okay, so if we've got a cosine of 1/2, then we've got a sine of root 3 over 2. In the fourth quadrant, we've got 1/2 and negative root 3 over 2. And in the second quadrant, we've got negative 1/2 and root 3 over 2. And in the third quadrant, we've got negative 1/2, negative root 3 over 2. So these are all 60-degree angles, these reference angles. All right, so if I were to look at them, this angle right here, angle of rotation in quadrant 1 would be pi over 3. I would have a 2 pi over 3 over here in quadrant 2. I would have a 4 pi over 3 in quadrant 3, and a 5 pi over 3 in quadrant 4. Now, let's isolate and make sure we know which one's which. So where is the cosine of x equal to positive 1/2? That's in quadrants 1 and 4. So it'd be pi over 3, that should be a 3. Pi over 3 and 5 pi over 3. And the cosine of x equals negative 1/2 when x equals 2 pi over 3 and 4 pi over 3. All right, outstanding. There are 4 answers. Let's look at example 11, and that should be it for today. Very similarly, we're going to take the square root of both sides. So sine x equals plus or minus 1 over root 2. Anywhere you see a 1 over root 2, you should be thinking factors of pi over 4. So where does that happen? Well, the sign is positive. Sign is positive in quadrants 1 and 2. Oops, that should be Roman numeral 2. There we go. So the sign is 1 over root 2 in quadrants 1 and 2, which means that x would equal pi over 4 and 3 pi over 4. Whereas sine of x is negative when in quadrants 3 and quadrant 4. Therefore, x is equal to 5 pi over 4 and 7 pi over 4. Okay, guys, one last thing that I'd like to note is this acronym, All Students Take Calculus. All that this means is what functions are positive where. So all trig functions are positive in quadrant 1, whereas only sine is positive in quadrant 2. That means cosine and tangent are negative. Only tangent is positive in quadrant 3, and only cosine is positive in quadrant 4. So all students take calculus. It's a good way to remember positives and negatives, and it'll help you along the way. That's it for 1.4 day number 1. We'll see you in the next video.